Okay, so I'm going to just do a really big sketch to help motivate the directional derivative here. There's a lot, I'm making this really big because there's a lot to squeeze in. Okay, so what I've got here is a vector in the plane called u. It's a unit vector. Okay, and I want to go ahead and u would just have components a, b. I didn't draw that very well. I don't like my a and b very well. I'm going to clean that up just a skosh. They just don't look, that A is really bad, and so is the B. What do you know? I'm going to get a little guidance from my axes here. So that's a right angle there, I think. Okay, so it's not great. Not great. Hmm. That'll work better, I think. Oops. better. Okay, so I'm just moving my triangle a little bit like this here. I'm not sure what all of that is right there. I forget. Move my A over like that. And then I'm going to finish my triangle here. Like that. Okay, and that's my unit vector U. Okay, so the U is still this AB vector. And what I want to do is come up with a smaller version of U that's going to be called HU. So maybe in a real fat pen and a bright color like red, I'm going to do a short version of U right here. So this red thing is going to be HU. Okay, and I'm going to break that thing down. And I think I'm going to make it bigger too. Pardon me for all the multiple tries that I'm doing here, you guys. Is what it is. Make it a little longer so that it's just more evident. Okay, so that guy right there in red is going to be HU, like that. And I'll move my U label down a bit. And let's see here. I want to break HU down as having components HA and HB. So I'm tweaking this as I go. Okay, so here goes. More of the same. Guidelines. I think this is all I need to do there for a guideline. And do this really thin and maybe in a faint color like that. Okay, so what I want is for the distance, this first distance here to be HA. And this other distance in the direction of B, I want that to be HB. And just clearly HU HU is going to have components HA and HB, like that. And what I'm trying to do is get a slope out of this. So I think what we'll do is we're going to come from this HU vector up and hit the curve up here. Okay, and then I'm going to connect that with a real dark tangent line like this. It's not really, this is more of a secant line here. Okay, so HU is basically going to be a displacement. I guess I'm going to do thinner. So HU is a displacement from where? Well, I guess this point that we start at here will give some coordinates. Let's just call that guy XY. Make sure that I don't need to do an X naught, Y naught. Yeah, we're going to do X naught, Y naught. Okay. So that's a starting vector. Let's get the endpoint of HU here. And so the endpoint there is going to be, I'm going to need more space for that. So pardon me while I move this outside like that. So that point over there is going to be the position vector X naught, Y naught plus HU. And if you work that out, it's going to be X naught plus HA, Y naught plus HB. Like that. HU is just the displacement. So if you're moving from one point to another. Now, these points up here are going to help me determine the change in Z. So on a surface, that's just going to be Z equals F of XY. The starting point is going to be Z coordinate there is going to be F of X naught, Y naught. That's just the height at this one point. And then I want to do a height at the other point. So right here, it's a different point. I'll say Z is F at this vector down here. Okay, so the X coordinate is actually X naught plus HA and the Y coordinate will be Y naught plus HB. Okay, so I'm trying to find the slope of that green displacement or that green secant line that I drew up there. So let's put this down below here and say that the slope of the secant is going to be F at X naught plus HA comma Y naught plus HB minus F of X naught Y naught. And then we have to divide by the displacement. Okay, so this would be the run down here. What's the run? I'll be changing that in a second. Okay, so the run would be the magnitude of HU. So maybe down below, run is the length of HU. Okay, but you know this is H. You can say the absolute value, but H is going to be positive. No, I'll just say the absolute value, that's fine. Absolute value of H times the magnitude of U. But U is a unit vector, so this is just H times 1, which is H. So this is the run that we need to put down here, just H. Okay, so the numerator is the rise, the denominator is the run. Okay. And if we take h to 0, then that's called the directional derivative. And so the derivative, why did I spell it like that? The derivative of f of xy at x naught, y naught in the direction of u is, and again, u is a unit vector. So this will be called d with a little u at f at x naught, y naught, like that. And we just need to take a limit on this secant. So we'll take the limit as h goes to 0 of f of x naught plus ha, y naught plus hb, minus f at x naught, y naught. Oh, that's the rise, the change in over the run, which is just the displacement in the x vector. Okay, so that's not something you can use to make computations. That's just going to be too hard to work with. So before you go, I'm going to try and get in the formula for making. This is an ugly derivative, and it's a derivative in a certain direction. And I guess we could say where u is the vector a, b, and the magnitude of u is 1. Okay, so this is an ugly, ugly definition. So for a working formula, oops, just let x be x naught plus ha, and y be y naught plus hb. Okay. We're going to define g of h to be f of x naught y, or sorry, f of xy. Using the chain rule, the derivative of g with respect to h would be the derivative with respect to h of f of xy but this would be fx times dx over dh plus fy times the dy over dh. That's a chain rule. But note, dx over dh, you're just taking the derivative of this, and the only variable there is h. So dx over dh is a. And dy over dh, again, y is up here. The only variable is h, so the derivative is b. Okay, so this is a times fx plus b times fy. Okay, now what we mean by this is fx at the coordinate xy. So I'm going to fill in a little bit more here and say afx at the point xy plus bfy at the point xy. Like that. Okay, and even more, let's say this is a times fx. X is x naught plus ha. Y is y naught plus hb. And then same thing plus b times fy at the same point. Like that. And then just note, this is g prime of h. Okay, so I filled that in up above. And then note g prime at 0 would be a fx. Now again, this is where h is 0. So this is x naught, y naught, plus b fy times, at x naught, y naught, because h is 0. So I'll make a note of this, h is 0. But also, g prime at 0 would be the limit as h goes to 0. The definition of a derivative would be like g at h minus g at 0 over h minus 0. And g of h, we said, is up above. So g of h is f of xy, but x, see up here, g of h is f of xy, way up there. X is x naught plus ha, y is y naught plus hb, minus g of 0. This would be f at x naught, y naught. Okay, and forgive me while I put a limit in front of this. That should have been done. So I'm going to squeeze in lim as h goes to 0. And this is all divided by h. But this is the definition of the directional derivative. So this is du f at x naught, y naught. Okay, so the theorem, you can see these are the same thing. G prime of 0 is expressed in two different ways here. So here's your theorem. This is our computational formula. For the directional derivative. Okay, and it's just du f at x naught, y naught, and we don't need the naughts now. Let's just say f of xy is a f at x at xy plus b fy at xy. And then we'll say off to the side somewhere, maybe in parentheses, u is the vector AB, and the magnitude of u is 1. But then you could rewrite this as just a dot product. You could say this is fx, fy dotted with AB, or this expression here, which is called the gradient of f. It's also called the total derivative of f, because it includes both partial derivatives. So we call it partial derivatives because they don't include all of the derivatives. The gradient does include all the derivatives, and the only way to do that is to represent it as a vector. So the total derivative of a function of several variables is actually a vector. Okay, so this thing over here, of course, the other vector here is u. And so the directional derivative, you're going to take this thing called the gradient, or the total derivative of f, and dot it with u. Okay, and that's it for the development. And thank you guys, everybody, for your patience. There we go. Okay, so first of all, let's just compute the gradient of f. So the gradient of f is the vector with the partial derivatives, making the total derivative vector, the gradient. So fx would be, let's see, first I would do a 1 over 2 times the square root. So you have a 9 minus x squared minus y squared there. And then you multiply by the derivative of what's inside, which would be a negative 2x. Same thing with y. Okay, so it looks like the gradient comes out to be just negative x over the square root. Comma negative y over the same thing. Okay. So that's easy enough. We will need to evaluate the gradient at our point. So the gradient of f at the point 2, 1. So this will be negative x, so that'll be negative 2 of the square root of what? So it'll be 9 minus 4 is 5 minus 1. There's the square root of, okay. Well, 9 minus 4 is 5. 9 minus 4, nice. And then a negative 1 over square root of 4. So of course, that's just negative 1, negative a half, I think. Okay, any questions about that? Okay, and so that's the gradient. And remember the directional derivative, I'll go up again. The directional derivative is just the gradient of f dotted with a unit vector. So we need a unit vector. Now that's going to give the direction. Remember, this is a directional derivative. I've got the total derivative. Now I need a direction. So the direction is 30 degrees up from the horizontal. Now I realize you might interpret this differently, so I want to make sure I draw a picture of this. at the point 2, 1 here, I can think of with a horizontal. I suppose I mean that I'm going out to the right and measuring up 30 degrees from that, like this. And that's supposed to be a unit vector. Okay. So any question about that? Right, so I need a u. Any vector could be written as an r cos theta, r sine theta, but it's a unit vector. So r is 1. Theta is 30 degrees. Oops. So we just have to figure out what the cosine of 30 degrees is. And I'm not going to make you type it because it has a square root in it. What's the cosine of 30 degrees? Somebody want to say it?
Square root over 3 divided by 2.
Thank you. Square root of 3 over 2. Square root of 3 over 2 and then a half. That's great. And once you have these, you have the gradient and you have the directional vector, you can do the directional derivative. So directional derivative is du, the derivative in the u direction of f at the point 2, 1 is the gradient of f at 2, 1 dotted with the unit direction vector. Okay. So that's easy now. So the gradient was -1, -0.5, and we're dotting that with root 3 over 2, 1/2, like that. And remember, dot products are scalars, as are slopes and rates of change. They are scalars. So you're going to do a negative root 3 over 2 and -1/4. And not a big fan of getting calculators out if we don't need to, so I probably would say -2 root 3 -1 all over 4 and just call it a day. Well, I don't know. Now that I'm done, I guess I'll get a calculator out. Not happily. -2 square root of 3 -1 over 4. So I got -1.12, I guess, approximately. All right, any questions?
So I have a question.
Yeah.
So the slope is only one, right? We cannot have like too many slopes. There is on that exact point is just one.
Oh, if I give a different direction, I'll have a different slope.
So what mean the other direction? Like,
well, okay, so this is a hemisphere. So let's see what we can do with this. Let's draw this. And the sphere has a radius of 3. Okay, I think I'm going to move that a little. Pardon me for a moment. Move it back I don't know why, I just don't think I have enough space. Not great, but there it is. Okay, so, and again, these are 3 because the radius of the sphere is 3. And the point is the point 2, 1. So here's a 2, and here's 1. Okay, so here's my point, just roughly right about here. Yeah. That's gonna look a little not great, so how do I do this? Okay, I'm gonna do a little bit more. Pardon me, I'm gonna keep tweaking this till I like it. I'm gonna do this the way I want to see it. So what I think I'm gonna do, I think this will help, is if I'm gonna put my x-axis way over here like that. So now if I go out to 2, you'll kind of see that. And then I'm gonna have my y-axis maybe go like this. So here's 1, like that. And so here's the point 2, 1. And I think I'll put my z-axis popping up here somewhere. And maybe I'll do that in a slightly different color though. Now I have a unit vector that's pointing 30 degrees up above the z-axis. So this is my unit vector I'm going to put in green, I think. So here's my unit vector here, like that. And then I'm going to try and draw sort of a dotted line from there up to a point on the surface like that. And here, there's like a tangent. So what I want to do is sort of want a tangent line to go through that. So I'm going to draw, I'm just going to draw a line. This is it -1? Okay. So I'm going to draw a line with a slope that sort of matches what I think a -1 slope should look like. And I have to move it into a correct position. So I'm going to move this, go through here like that. And what I'm trying to do is to show that this direction vector is pointing in the same direction. So what do I do? How do I do that? I'm going to move my direction vector just a little bit. Because what I want is to have that, the shadow of the line that I drew, which is a tangent line, I want that the shadow to fall on my vector. So I'm going to do my vector this way. This is u now, like that. And I'm going to make the shadow of the other vector sort of like this. So the slope of the blue line is the directional derivative. So that's the negative 1.12. And that's not a perfect drawing, but you just have to understand that if you face a different direction, you're going to get a different steepness. Okay, so let's say we change the angle to 45 degrees. So let's just redo this. So change the direction to 45, 45 degrees up from the horizontal. So the unit vector now is going to be cos 45 sine 45. And everybody knows what that is. I'll do root 2 over 2. Like that. Oops. And now the directional derivative would be du f at 2, 1 again. Still same point. But you're going to take the gradient of f at 1, 2 and dot it with a new direction. And that will give a different slope. So the gradient of fcz, that was the 1, negative 1, negative a half. And you're dotting with root 2 over 2, root 2 over 2. And I'm going to squeeze this in. So that would be negative 2 root 2 over 4 minus negative 2 root 2 minus root 2 over 4. So I think it's negative 3 root 2 over 4. Like that, I think. I hope. And so that's a different value. So that's a steepness of negative 1.06. So it's similar in steepness, but it's different. So I'm trying to squeeze that in here. Okay, any questions? Okay, any questions? Different directions give different slopes. You can go straight up a hill or you can go kind of at an angle and it might be easier. Okay, let me see what else we've got here. We got a little bit of theory. First thing is just to sort of do a little math. Let's first begin by letting u vary. Okay, remember, u is just a unit vector pointing in any direction now. Okay, so we're thinking about all the different unit directions you could come up with here. And the derivative in the u direction of this function is just the gradient of f, which we're not letting vary, dotted with u, which we are allowing to vary. Let me go ahead and mark my theta on this diagram. So I'm going to put in my theta here. I don't know if you can see that. That's better. Okay, so it's the gradient of f dot u, but we know a lot about dot products. So we can say, oh, well, that's the magnitude of the gradient of f times the magnitude of the unit vector, which we know is going to be 1, times the cosine of the angle theta, which I've denoted. Wait a minute. Theta has to, forgive me, but I'm going to go ahead and fix my diagram because theta is the angle between u and f. So I'm going to find the gradient of f. So let's have our gradient be like this, and this will fix the diagram. Like that. Remember, u is varying. But gradient of f is fixed. Okay. So anyway, the directional derivative is the magnitude of the gradient of f times the magnitude of u times the cosine of the angle theta, which separates those two vectors. Okay. Magnitude of u, as you know, is 1. It's a unit vector. So this is just the magnitude of the gradient of f times the cosine of the angle that separates them. Okay, so du, these are notes. 1, du f at xy is largest when? What angle? Yeah, theta is 0. Thank you, Bilal. So when theta is 0, that means u is pointing in the direction of the gradient. Okay. So let's say when u points in the direction of the gradient. Okay, so that is to say, gradient of f, I always think of this as like a compass that doesn't point north, but it points in the direction where the hill is steepest. So gradient of f points in the direction of maximum increase on the surface. On the surface z equals f of xy. It's a compass. It just points. This will take you up the steepest part of the hill, which is sort of a bummer. Okay. In that direction, the maximum value of the directional derivative in that direction is what? Can you say it out loud? You don't want to type it. In that direction, we said theta is 0. So what's cosine theta? Well, cosine of 0 is 1. So the directional derivative in that direction of maximum increase, where cosine theta is 1, is the magnitude. Yeah. Sorry, I beat you to it. Magnitude of the gradient. Magnitude of the gradient is the steepest slope on the surface. And the direction of the gradient is the direction of that slope. So it's a kind of an interesting vector. It holds multiple bits of information, the direction and the magnitude of steepest slope. Any questions? Well, great. So how do you find the direction of maximum decrease? What's the angle now? How do we find the smallest value of the directional derivative? So let me go ahead. It's this 2 du f at xy is minimized when u points where? So I don't know if you guys caught the video. It looked like it was jumpy just now. I'm asking where does u point to minimize the directional derivative? And all you have to do is look at this expression here. Opposite direction. Yeah, so that's where theta would be pi, or 180 degrees, which is the opposite direction of the gradient. So when u points in the direction opposite, oops, of the gradient of f. So what we're going to say is then from this, the negative of the gradient, this is sort of obvious, I think, negative of the gradient of f points in the direction of maximum decrease for z equals f of xy. Okay, yeah. All good answers in the chat. Thank you, Jingyi. Oh, sorry, Xiaohui. And then we're kind of talking about the slope. What is the minimum value of du f of xy? Anybody? And you're gonna have to say it out loud, I think, if you want to say it. We see the directional derivative is the magnitude of the gradient times the cosine of theta. And when theta is 180 degrees, the cosine will be -1. So that's the smallest this could be. when cos theta is -1. Doesn't get any smaller. So that would be the negative of the magnitude of the gradient. That's the minimum value of the directional derivative. So you say it's the negative of the magnitude of the gradient of f. Okay? Now, let's have a third comment. du f of xy is 0 when what? Good, Bilal. Thank you for that answer. When theta is 90 degrees. So when u is perpendicular to the gradient of f. So the slope would be 0 here. So the slope is 0 in this direction. So motion in this direction would be on what kind of a curve? If the slope is 0, what is your path if you're moving in that direction? What's the name of the curve if you maintain a slope of 0? So you're on a hill and you're walking along it and the slope is 0. We had a couple names for that. One of them was a contour. The contour on a hill, when you move on it, is perfectly level. The hill's not level, but the path you're on does not go up or down. There's another name for that. Should I step back? Let's see, let's look at 14.1. I think we have something in there. Remember this? Oh, I've got a little bit of a slow connection, I see. So I have to pause to wait for the video to catch up. I'm going to stop the share for a second. And I'm going to start it up again. Yeah, equipotential surface almost, but not quite. Remember, a curve that does not go up or down is called a level curve. It's also called a contour. Okay, so if you're moving along a level curve, then you're moving in the direction that is perpendicular to a gradient. So let me see if I can go back without too much trouble and get back into this. Looks like we're good. Okay, so the slope is 0 in the direction, in this direction. So motion in this direction is along a level curve. what I wanted to get out of that. Therefore, and this is the big point I want to make here, the gradient vector is perpendicular to level curves for a surface. So the gradients of z equals f of xy are perpendicular to this surface. Okay, so when we had z equals the square root of 9 minus x squared minus y squared, like that. That's a hemisphere, as you remember. Like this. Okay, now the gradient vectors will be two-dimensional. So they live in the xy plane. I'm going to do a little adjustment here. I want to center this better on my origin. That's pretty good. And I'll put in a z-axis, I guess. That's not that great. Okay, so, and then what I wanted to do is to draw level curves on this thing. So I'll do that. That's terrible. I'm gonna have to do a better picture than this. So this is a level curve, like that. Okay, and so on. And then let's put this into the XY plane. First of all, I'll draw my circle. That is okay, I guess. That's not great, but let's see, I'll do one more. Having trouble. Here we go. Okay, so these are level curves. And remember, the level curves point in the direction of maximum increase. Sorry, forgive me, the gradients point in the direction of maximum increase. So maximum increase points to the top of the sphere. So maximum increase has got to point up the sphere. But again, gradient vectors are in the plane. So they're going to be biggest where the curve is steepest and always pointing in the direction of maximum increase. And it just turns out that's perpendicular to the level curve. So right now I'm just drawing a bunch of vectors that are gradient vectors that are pointing toward the origin, because that's the direction of maximum increase. That's how you get to the top of the sphere. You have to move toward the origin, in this case, because that's where the top is. And I'm drawing big vectors right now because the slope is pretty steep. As I get closer to the top, it's not as steep anymore. So I'm going to get this right. Come on. Try that again. Trying to get this thing to turn into a line. It's not great. Okay, I think I'll just do this like this. So these get smaller because the slope is less steep. Remember, the magnitude of the gradient is the directional derivative. It is the slope in the direction of maximum increase. I'm drawing perpendicular to the level curves. Okay, at the very top, the slope is 0, so the gradient will be 0. Okay, so let's just make a note. These are gradient vectors. Always perpendicular to level curves. Okay, I'm just gonna pause there and bring up my chat, see what kind of questions I have. I figured it out, Alicia says. Okay, so that's something else. I don't know what you figured out, Alicia, but we're just gonna let it go. All right, any questions about what I've presented here, what the gradients do? Like I said, they live in the plane, but they tell you, they're like a compass. It has to be level. Gotcha, Alicia. They're like a compass that has to be level. It has to point to the gradient. I'm gonna pause for a second on the recording. Okay, so we've got the gradient vector here first. There. And this guy is r prime of t. The gradient of f is perpendicular to r prime of t, which is tangent to a curve C contained in the surface. Sorry, contained in the surface. So I've got the gradient perpendicular to curves. Also notice so I'm just gonna say the gradient of f is perpendicular to any curve C. That passes, or let's say, yeah, let's say that passes through the point x, y, z. So that's sort of complicated. You remember C was arbitrary. So let's think about this. I'm going to bring my picture down from up above. So hang on just 1 second real quick. And I'm going to do a little cleanup to get all these words off of it. Okay, so what we're saying here is that the gradient is perpendicular to every curve through this point. That's contained in the surface. If the gradient is perpendicular to every curve in the surface, it has to be perpendicular to the surface itself. So let's make that note here. If gradient of f is perpendicular to every curve in this surface, containing the point xyz, then the gradient of f is perpendicular to the surface. At the point xyz. Okay, so I'm going to go ahead and sort of sketch that in then. I'll do a little perpendicular symbol there. Okay, so maybe just a couple comments, then we'll take our little break here. If z is equal to f of xy, then the gradient of little f is perpendicular to level curves f of x, y equals c. So we've already established that. Okay, and then the new fact is if, let's say, w is f of x, y, z, big F with 3 independent variables now, then the gradient of big F is perpendicular to level surfaces. Big F of x, y, z equals a constant, which I was calling k. I'll go ahead and use a c now. Okay. I've already drawn what that looks like for level curves. For level surfaces, I think it's easiest just to try to draw a ball. So I'm going to just do a sphere. And I'll put a hemisphere around it. Never ceases to make me laugh when that happens. See, that's a great ellipse. And look what it did to it. I'll try one more time. Yeah, when I do a bad job, it does a good job. I don't understand that. Okay, so that's a sphere. And what I want to do is find the center. Let's see if I can find the center of it. I'm going to do a little doodling real quick here. Oh, that's not good. So I'm just looking for the center of that sphere real quick. So pardon me while I do a little bit of work here. Just trying to snap to the center of this. I know that that's right. Okay, and then what I want to do is I'm going to draw little radii coming out from that center. And these are going to get erased. So these are just guidelines. So don't get too attached to them. Okay. My point is to say, wherever I pick a point on a surface, if I draw a gradient vector, it'll be perpendicular to the surface there. Okay. Oh, and where's this going? Yeah, this might point outward. I think this will probably point outward. It could point inward. All I know is it's perpendicular. And the gradient can be evaluated anywhere on a surface. Okay. So wherever you are, the gradient will come out differently. It will be perpendicular to the surface. Okay? Do a little bit of erasure now. Maybe, I think what I want to do is put a coordinate system on this real quick here. I don't want to do that. Now I'll put a coordinate system in just for the heck of it. Okay. Any questions? Looking for them, don't see any questions. I'm going to flip through my notes to see if I missed anything important. Yeah, so I'm gonna call it quits. I think I got the most important items out. Oh, except for one more thing. One more thing. Just a bit of a review from the past. This goes to tangent planes real quick. So with tangent planes, remember when you have z equals f of xy, at x naught, y naught, we said that fx at x naught, y naught, and fy at x naught, y naught, that those could form coefficients for the x minus x naught, so that's the slope in the x direction, plus the fy is a coefficient for y minus y naught, so that because that's the slope in the y direction, and then you add in a z naught, and this is a tangent plane, so z equals that. Okay, but we also have a new piece of information that can give us another version of a tangent plane for an implicit function. So this one was an explicit function. I'll say explicit z. Okay, and I made a note down here that z naught is f of x naught, y naught. Oops, my bad. Okay. But let's say for an implicit surface, let's say big F of x, y, z equals c, the tangent plane to a point x naught, y naught, z naught has normal vector. What should we use for the normal vector?
Professor, we can't see your screen.
And that's nothing at all? Or is it just not
Well,
updated?
just whatever you wrote for the implicit.
Yeah, that's a shame because it's like the internet is lagging right now. So let's pause for a second. I think it works best if I just stop the share and restart it. Thanks for letting me know. So that's what I was writing there. Okay, so it says for an implicit surface, f of x, y, z equals c. Maybe you can't solve for z. And we still want to be able to do a linear approximation to the surface. And we know that planes need normal vectors. So, and we know that the gradient of an implicit function, a function of 3 variables is normal. It's perpendicular to the level surface. So this thing here, f of x, y, z, is a level surface. And you could do a normal to that surface to be gradient of f at the point of tangency, which would be x naught, y naught, z naught. Okay. And if you just called this a vector A, B, C, then the tangent plane is just A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. That's how planes were first introduced. You just needed a normal vector. Well, the gradient to a surface, to a level surface, is normal to the surface. So use that as a normal and then just do a normal equation for a tangent plane. Okay. Maybe we could do a real quick example and then we got to take our break. So the simplest, let's just do a sphere. I'm going to do x squared plus y squared plus z squared equals 14. And the point I'm hoping will be 1, 2, 3. Just double check. 1 squared plus 2 squared plus 3 squared better be 14. And it is. So we know that this point is on the sphere. Okay, my f is this thing, big F of x, y, z, equals 14. The gradient of f has components, you know, big Fx, big Fy, and big Fz. Which will just be 2x, 2y, 2z. Any questions? And then, of course, so big F, sorry, the gradient of big F at the point of tangency, that point would be 1, 2, 3. Is just 2x, 2y, 2z, so this will be 2, 4, 6. And this is your normal vector. Because does that make sense? Now you've got your normal to the surface, so you just do a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And now you can say, well, that's 2 times x minus 1 plus 4 times y minus 2 plus 6 times z minus 3 equals 0, and etc. I'll let you finish that. So that's for implicit surfaces where it's just too much trouble to solve for z, or much uglier to solve for z. That actually is real nice. Okay, I want to stop the recording, and we'll take our break now. And I'll take questions after the break. Sorry, I didn't mean to stop this share. Let me put that back up. Okay, but I will stop the recording.